Hello, can you guys hear me? Microphone test. 1, 2, 3.
Loud and clear. Hi. Yeah, glad to see you, Ming-Yu. Yeah, I've already missed you because you know what? You're not using Sarah's name here.
Oh, I'm using Sarah's here?
Yeah.
Oh,
I'm
okay.
looking for you for a while. I mean, I'm so worried about you.
Oh, sorry. I didn't know that I log in with Sarah's name. So, sorry. Should I log in again with my name?
Oh no, it's fine. It's fine. We know you, so that is totally fine. Sure. Yeah. Let me quickly introduce a bit about Ming-Yu Liu. So all right. So let's see. All right. So Ming-Yu now is a distinguished research scientist and a manager with NVIDIA Research. His research group focuses on deep generative models and their applications. They have created several high-impact research works. Several of them have enabled exciting new products, including NVIDIA GAN and NVIDIA Maxine. Yeah, now below is a little bit about the advertisement. So he is currently looking for talents to join his team. So you can just DM his NVIDIA email if you're interested in or you're passionate about generative models and their applications. So prior to NVIDIA, Ming-Yu was a principal research scientist with Mitsubishi Electronic Research Laboratory. So in short, MERL. I think that is in Cambridge. He received his PhD degree from the University of Maryland, College Park, MD, USA in 2012, advised by Professor Rama Chalapa. Okay, so I know Ming-Yu long before when I was an internship at MERL too. Maybe you remember me somehow. It was back to 2014. Ming-Yu was very nice and very knowledgeable and very, willing to help young researchers. So he has been my career model for a while. So welcome Ming-Yu to our workshop, and also welcome his exciting talk. The talk title is about phase VID to VID and the GANcraft. So welcome.
Thanks for the nice introduction, and glad to see you again. And thanks again for inviting me to give a presentation here. Let me share my slide. So I'm gonna share my entire screen with the audio, and I have some video clips and gonna optimize for video clips. Okay. Is my slide visible?
Yes.
Okay. So yeah, today I'm gonna talk about two works. The first one is phase bit-to-bit, which the paper title is one-shot preview neural token head synthesis for video conferencing. And this paper is published as oral paper this year, CVPR. So, and Tinjun, the lead author, gonna give a presentation on Wednesday. And after the phase bit-to-bit, I'm gonna talk about another project called GANcraft. That one is more on neural rendering of Minecraft scene. Okay, now let's dive into the phase bit-to-bit. So I want to start give a little bit of motivation. And now we are using video, using the Zoom app for video conferencing. And because of the pandemic, video conferencing has become the routine, actually, the way we communicate with each other in the modern day. Just last week, I spent about 20 hours in video conferencing. And you can also see this excitement from the stock price of Zoom. It's just increased by 6 times in just 8 months. And there are many great video apps like Teams, WebEx, and others. Okay, so video conferencing is important. And often we want to have many people join a video conference call. And when you have many people, everybody wants to stream their video, then bandwidth is an issue. So yeah, so I mean, although the broadband has increased its bandwidth, however, when there's more demand, it's still not enough. And Also, in some places, infrastructure could be very poor. Not everywhere have high-speed internet, especially in mountain area. So bandwidth is still an issue. And when we look at a bigger scale, not every country is like a developed country has a high-speed internet. Many places the internet speed is still low, and also usually the upload speed. So here we have the green curve, which is the download speed, and the blue curve is upload speed. And you can see the upload speed is still pretty limited. If you want to have a video conference call with another, the upload speed gonna limit the amount of visual information you can stream to the receiver. Also, eye contact is an issue, right? I mean, we are using video conferencing to simulate the virtual interaction experience. However, we look at the screen, try to look at the other person's face. That's how we are trained to communicate with each other, from the school day. But the camera might be located at a different place. So although you're trying very hard to give eye contact, but you are not looking at the person. And fortunately, this is a well-recognized issue. And a couple of companies has come out with a great solution. They basically rotate the eyeballs, change the eyeball location to make it looks more like looking at you. So you can see the before and after from this Intel, Microsoft, and Apple's software, and the eye contact is better. This can solve the problem to some extent, but I think many of us has a dual screen setup, and sometimes you have the window and the camera located at different places. Like the two pictures shown here, both of them are trying to look at the other party in the screen, trying to give the right eye contact, but the camera is located in different screens, so it doesn't look like they are paying attention to the other. And so this is not desirable. And the gate correction one, the eye contact correction one I showed in the previous slide does not solve the issue. So yeah, so now we have two problems in mind for the video conferencing. One is the bandwidth is limited, and the other is eye contact is an issue. And since the pandemic, we have been starting to think about how we vision researcher can help to improve the video conferencing. And then through a year's effort, we come out with the Facebook algorithm. So here we show a couple of animation, and just to give you an overview of what this Facebook is trying to achieve. The first, the top left here, you have the original input video, and we set a very low bandwidth. So we set the H264, which is a common video codec standard, and use the low bitrate to transmit the original video. This is uncompressed one, this is compressed one. And you can see that the visual feature is barely visible, recognizable in these low bit rates. However, with the Facebook algorithm, we were able to reconstruct the facial detail kind of faithfully using the same bit rate. So the same bit rate, H264, is not visible, and ours is pretty good. The second is this algorithm also allow you to rotate the head, the face, based on your desire. It's also rotate the gate. Later I'll show a demo video, but you can think that as I'm a receiver of the stream, I can redirect the sender face based on where the window, the video conference call, the app, the window is, to kind of give a better eye contact. And another great use of this algorithm is for photo animation. Instead of streaming your video, we can use the motion extracted from the video to animate a cartoon character. Notice that this is just a 2D image. We don't have the 3D model, and so it's quite convenient. Okay, so we're gonna show you an algorithm that can achieve these three tasks at the same time using the same trend weights. All right, so the key, the core of this algorithm is a neural talking head model. So neural talking head model is a talking head model. Talking head model is a model that synthesizes talking head, just face and head region only. Instead of stream the compressed visual information, we stream some parameters to control the talking head. Yeah, so that's the key idea. And there are many talking head models, neural talking head models, and they can be roughly divided into 4 categories. So on the top, each column is based on person specific or person agnostic. Person specific means that that talking head model only work for the person. Maybe you only use that person's video, or you have the 3D model that is tuned for that person. And person agnostic means that you could use it can be used for different people. Ideally, you just need a photo of that person, then you can generate that person's video. And based on whether they use 3D model, that's a 3DM based, and there's also pure 2D. So that you have many different neural talking head model. And I just want to mention that this is by no means a complete list of neural talking head model. I think it's a very popular topics, and just there's a couple of examples here. And for this first bit, it's gonna be in this category. It's gonna be person agnostic and the pure 2D. Yeah, so you don't need a rendering engine to help render the talking head. All right, and here I want to do a simple comparison between person specific and person agnostic. So person specific means a model for everybody, and person agnostic means for each person you need to have a model, right? And I would like to argue for video conferencing, you do need a person agnostic model because it's for person specific, you need to train a model for each person, and training will consume a lot of time, and it may not converge. Yeah, so, and also it makes deployments more complicated. I mean, it does have its benefits. Usually person specific model can achieve better quality, and for creating, for more quality demanding application, you want to have person specific model. But for video conferencing, you do need to have a person agnostic model. And the flexibility is a person agnostic model. All right. So now let's talk about the high-level idea of flexibility. So let's say we have a video, a driving video, and let's take the first frame as the source image. We call it source image. Recall in video compression, they have I frame and P frame. You can think that the source image is I frame. Okay. For source image, we extract something we call appearance. It describes the rough geometry of the subject, the color, the skin, the hairs, the style, appearance. And for the driving video, we're gonna extract for each frame, we're gonna extract expression and head pose. And we're gonna show you an algorithm flexibility that by combining the appearance and expression and head pose, you can reconstruct the video. And if you don't like the head pose in the original video, you can change it to something you like for the eye contact. then combine the appearance from source, expression from driving, and your own specified head pose, then you can achieve phase redirection. And we're gonna call these information key points. And we're gonna show you that this information, all the motion head pose information can be represented by roughly, I think it's about 80 bytes. So and each frame is represented by 80 bytes, and it's then with this very compact representation, you can stream your video to the receiver, utilize a very low bandwidth. Okay, now the key for such a neural token head synthesis is to build good correspondence. So what it means is that remember here we have a source image, right? Source image has a lot of information about the subject, and when we want to reconstruct the video, right, we want to borrow as much information from the source image as possible. In the video codec, in the traditional video codec, they will use something called motion field estimation. But here we're gonna use some kind of sparse correspondence to do that. But the idea is if you can borrow this region to synthesize reconstruct a frame at different time, then you should borrow it. But there will be places where you cannot borrow. For example, this subject, this image doesn't have this subject in with a closed eye. But the next frame, the eye might be closed, right? And you don't see the closed eye in the subject. Now you need to hallucinate. In traditional video codec, you will send something called residual, basically the error after apply the motion field. But here we're gonna just hallucinate. Yeah, and that is useful because you don't need to send residual. You further reduce the bandwidth. Right, but the key, okay, here, so basically by figuring out a way to diverge previous information correspondent hallucination, and we can represent the video using a more compact representation. All right, so let's talk about the method, the source image, the driving image. We will first extract 3D source key points and the driving key points, 3D key points from single image. And I'm not going to talk about it, but the way we learned the 3D key points was using self-supervised learning with some kind of key point equivariance loss, and which has been a popular approach for key point estimation. Yeah. And with these 3D key points, from the correspondence between the key points, we can build a 3D flow field. And this is gonna be a sparse field because you only have few key points. But from this sparse correspondence, you can expand to get a dense field. And with this field, you can warp the source features to put the eye in the right location, hair in the right location. And then you can use a generator to generate the output. And for the place that you cannot warp, usually you, I'm skipping the step here, but there's a additional step to estimate the occlusion region, occluded region, and the generator can leverage that indicator to figure out when to hallucinate. And okay, and then so by combining the correspondence and hallucination, we can generate an output image. All right, now this seems to be pretty common. I think the key contribution of this method for the neural token head is how we represent the 3D key point. We are actually use a decomposition to represent the key point, and this decomposition is learned unsupervisedly. All right, so let's dive into the detail how the 3D key point is extracted. For the source image, for the key points, we actually have two branches. One is called identity branch, the other is post branch. For the identity branch, we use something called canonical key point detector to extract the canonical key points. And these key points is for decoding, encoding the shape of the subject, like the shape of the nose, the shape of the face. It doesn't contain expression or pose, meaning that when you rotate the head or you change the expression, the canonical key point should be the same. And the expression and the head pose is actually extracted from this pose expression estimator. Yeah, so we have the rotation angles, 3 angles, and the translation vector, 3 scalars, and also expression deformations. We actually use 20 key points, and each key point in 3D, so you have 60 numbers here. All right, and the combined, we have the source key points, the one we use for building the correspondence, right? And for the driving image, because we know that it's gonna be from the same person, so we don't need to apply the identity branch again. We just do pose expression estimation, and we have this head pose angle, translation vector, expression deformation, and by combine with the canonical key points, then we have these driving key points. And earlier slide we show how we use these to do learn the motion field, right? So now we have them. All right. So now let's of course this is the same module, so shear weight. So now let's take a look on the function of each element here. So so for the source frame, this is a canonical view. This is a reconstruction if you purely using the canonical key points. If you purely use the canonical key point without applying the translation, rotation, and the expression, right? So this is what you get. And now for the driving frame, we have extracted the head pose and expression. And by applying the head pose, we rotate it, and apply translation, we shift it, and apply expression, we change the subject to the correct expression. Yeah. All right. So now let me talk a bit more on how we build a video conferencing system using this neural talking head model. So the source image will be like the iframe in a video codec. We just send it using the standard image compression method. And the key here is how we send the driving image. For the driving image D, right, we process the frame independent of other frame. We first extract the head pose, rotation, 3 angles, translation vector, 3 numbers, and the expression deformation, 20 key points, each one 3-dimensional. And these numbers can be further compressed using some entropy encoder. You can choose Harman coding or arithmetic coding, and we use arithmetic coding. And actually, if you don't do it per frame, you do it by every 2 frames or 3 frames, you can use some more advanced coding scheme to compress further down. Yeah, but this is not our purpose, and there are many coding schemes in the literature. So it's something that you can explore if you are interested. And now we compress the key point to very tiny bits, and then we send over the internet, and we apply entropy decoder to recover the head pose, translation, and expression deformation. Oh, okay. Now we can then reconstruct this driving image, the reconstruction called Y, and we use the source feature here. And sometimes you want to specify your own head pose. Yeah, so that's how we reconstruct the driving image, and we do it per frame. And if the model is super powerful, ideally you just need to send the one source image, and all the subsequent frames you can just send the head pose, translation, and deformations. Yeah, and this gonna give you a lot of bandwidth saving. And here is our experiment results on bandwidth saving. Here we see 3 plots. The the middle and the rightmost plots are user study. We'll start with the leftmost plots. Because this task is a reconstruct the face, right? And this is more like people in multimedia call this semantic reconstruction. So you just want the semantics to be correct. You don't ask for pixel pixel alignments. So a good loss to use is the LPIP loss or perceptual loss. There are many implementations. We use this one from Richard Zhang, published in 2018. So the lower, the better. The y-axis, the lower, the better. You want a low perceptual loss. And the s-axis is the bits per pixel. So in average, how many bits you need to represent a pixel. Yeah, of course, you want to have as low as possible. So, and we construct a benchmark data set contain, I think, about 200-300 long videos. And we compare to a couple of different algorithms. From the traditional video codec, we have H264 and H265. And it's a first order motion model from Sergey, the previous keynote speaker, and Fuchsia bit-to-bit, our previous paper. And for our method, the fast bit-to-bit, we have two schemes. One is use fixed 20 key point, the other using adaptive. I'm not going to talk about how we do adaptive, but the key idea is sometimes when the expression change is small, we don't need to send that particular key point, so we can save additional bandwidth. And for the codec, they allow a number parameter to specify different compression rates. This is called CRF. So we vary the compression rate to produce a curve. And we find that using our methods, we can achieve low perceptual quality, high perceptual quality, but with much fewer bits. And we did a user study compared to H264. And we found we basically present two videos to the Emerald Mechanical Turkers, SN to choose which video is a better reconstruction of the original video. And so we have preference score, the preference that the Turker choose our over the H264. And found H264 have a different CRF number, so we compare to different, and we found that ours is roughly comparable to the 36. And if you plot the number 36 here, the bits per pixel is 0.016784, and ours is an order of magnitude smaller. That's how we achieve 10x bandwidth saving over H264. With the differential coding, you can achieve 20 to 30, actually 20 to 50 time saving, but I'm not going to cover the detail here. Okay, so earlier I mentioned the head and eye contact is an issue. You see the earlier method from Intel, Microsoft, and Apple, they can rotate the gates. Here we show how we can rotate both head and gates simultaneously. These people are chasing the star. And sometimes it's more convenient to rotate the head. Sometimes just you just need to rotate the gates. And we actually have API for people to play. And later I will show you a website where you can give a try. It's an online demo. You just need to upload your photo and you can start to rotate your head and gates. All right. So earlier I mentioned that we can animate to the character, right? The idea, remember that we have a source image. The source image doesn't need to come from that person. It can be coming from a different person or a cartoon character. And with that, you can animate this cartoon character. Here we show the StyleGAN generated cartoon character. And by using the driving video from a real video, it trains the motion, we can animate the cartoon vector. So we have StyleGAN to generate cartoon, and then we can animate them using this fast bit-to-bit. All right, and also I want to mention that the driving video earlier here, the source images from is a synthetic one, right? It's generated by StyleGAN. And here we're gonna here the source images can be from style GAN or from real people, and the driving video can be as simple as like this simple CG model, no texture. So here the motion here gonna be transferred to these photos, and we have.
We're going to play a wonderful game called Who is Your Daddy and What Does He Do?
Yes.
We're going to play.
All right, so here I'm gonna conclude the first part, the face bit-to-bit parts. It's a neural talking head model for video conferencing, and it can do three things: face video compression, face and gate redirection, and photo to the avatar animation. The code is built using the imaginary repo. It's available here, and because our product team is commercialize this method, so we are not yet ready to share the model. But if you want to play with the model, they will have SDK for you to use. So check out the Maxine website here to get access. And also there's online demo. You can click and you can play with the interactive demo to change the face. Redirect the face. Yeah. All right. So now I think I'm gonna talk about the next topic, GANcraft, which is the paper title is unsupervised 3D neural rendering. Actually, I forgot the R here. Rendering of Minecraft worlds. Yeah. So Minecraft is a very popular video games. Many kids, they play Minecraft. It's a game of creation. You have some building blocks, the fundamental building blocks, but you can use them to build a very complicated world. And this one example, and here are the number of players in millions. You can see many people play that, and I know many of my friends play this game with their kids. So earlier we have a paper called GAN, which is about converting segmentation mask to photorealistic images. So you have segmentation mask either extracted from a real image or painted by a user. Using the network, you get a photorealistic image. After that, we have been thinking about how do we extend it to 3D world. Instead of converting an image, we want to convert a world to a semantic world to real world. A semantic world that you can easily build like a segmentation mask, and the Minecraft is clearly one very good tool to build a 3D world, right? The world conversion is this, you can call this image to image and here world to world. World to world is much harder because you need to support different camera trajectory. And also instead of render image, you're gonna render video, right? So the tempo consistency is important. Right? You can say that when you change a different view, the color should change completely, right? The consistency need to be kept. All right. And there are challenges. So first of all, this is some kind of 2D projection of Minecraft world. So basically, each Minecraft blocks have a semantic class, and each semantic class you assign a color, like a tree is green and the ocean is blue, and you take a 2D projection of this semantic world, and you have these semantic images. These are semantic images from Minecraft world, and they are very different to the semantic map you would extract from real world photos. First of all, real world photo tree is never blocky in real world, right? But Minecraft world, the tree are blocky. Yeah, and to mention the label distribution mismatch. So this is one change. No corresponding real image for Minecraft world. And the second image is we need to have consistent outputs. This is from Munich algorithm and unsupervised image-to-image association algorithm. Each frame may look real, but when the camera view change, you see a lot of jittering. Yeah, so this is not ideal, right? So this doesn't mean doesn't suggest that you capture the concept, you capture the 3D, you don't have this kind of view consistency. So the GANcraft is developed to solve this problem, and here I'm gonna just tell you how we achieve it. We use a voxel wall representation. So I mean this derived from Minecraft. This voxel word, right? We have a feature vector for each corner. Okay, and when we want to convert a ray to a color, so we first do projection and to get simulation mask. And what we do next is to use spade. Spade is the method behind Gaussian converting photo segmentation mask to photorealistic images. So this is sky to sky, you know, ocean to ocean. Yeah, you generate something we call pseudo-image. So this is not a real image. It's generated by spade, but segmentation mask is better matching the segmentation mask here. All right. And we use a neural radiance field, so something that's made it popular because of the NeRF work. So we sample for array, we sample endpoints from the voxel, and these are the voxel, and for each of them we compute the feature, and we aggregate them, and finally we get the feature per pixel. This is not the instead of directly compute the color, we get a feature. Here, right? And with these 2D features, map of 2D feature, we use a convolution neural network to convert it to a real image. And notice that these real images has a different style to these pseudo-image. And what to capture the potential style of pseudo-image image, we actually apply a style encoder to encode the style and feed the style information to the CNN and this NLP step. And we use several losses to supervise the training. First of all, we want the output image to look real, and it should match the pseudo-image. And we have tried a couple of them and found the combination the best. You know, minimize the VGG distance between these two images as well as L1 and L2. And also we want the output image real, so we apply another GAN discriminator here to measure the output looks like a real image. So real image is used here, right? The real image is first used to train this spade model and later used again to measure the output image looks real. And this is some video results. This is a Minecraft world, pretty blocky. And then we convert them to photorealistic output. And so we basically have a huge world, right? Not only we respect the structure, but we also try to get the tiny details like the flowers, grass. And here is the, I think it's the same one. Here's another example. The video is available in our project website. You can take a look at here. I think because of the room, there's some additional artifacts. So you can see we convert them to photorealistic. It's not yet perfect. You still see a lot of blocky artifacts. Later I'll discuss a little bit how this can be further improved. All right, so this is another world. And this is a world with deserts. And we can also change the style. yeah. So gonna give a conclusion on this part. This is a neural renderer for Minecraft world. It's based on neural volumetric rendering plus GAN. And the initial result pretty encouraging. But what we do now is we train a word at a time. So it's a word specific. So it cannot be applied to a different Minecraft world. And what we have been working on is to make it feed forward so that a model can be applied to different world. And we also try to remove the blocky artifacts. The blocky artifact coming from the voxel is blocky. The input geometry is blocky, and we have been investigating how we can refine the voxel world first before doing the rendering. And we currently only support, I think, about 13 object classes. Eventually, we want to support also like animals, humans, something interesting. And make rendering faster. Now each frame takes 10 seconds. So it's not fast enough. And also the object might move. So we also want to support moving object. In our plan, we're gonna release the GANcraft code and gonna be released in this imaginary repo. Yeah, all right. So this gonna conclude my presentation, and I think I'm ready to take questions. Oops, how do I stop sharing? Hello.
Yeah, so any question from the audience? I think it's a question time for the keynote speech. Anyone? All right, so I'm gonna contribute a quick question, Ming-Yu. So I think the demo is very impressive. So for the work, the two works, so that will be released to the NVIDIA product. So which one? So where can we find it? For example, you said there will be SDK, so that will be part of the deep learning library or the graphic card?
It's gonna be a library or something that's support your API so that you can. I'm not.
Oh,
really
I see.
Yeah.
Sure. Yeah. In case in future we can enjoy this fancy function. So.
So it's yeah. Well, I know people have been reproducing the results. You can
Right.
check the project page. I think some person has successfully reproduced the result, and they're gonna release their code. Yeah.
Sure. That would be great. So another quick question is about the computation overload. So overall, so we just want to know, for example, for researchers who want to follow work, there will be a lot of, hardware requirement like GPUs, hardware resources, if they want to reproduce or follow your work. So is that a lot, or it's just a regular workstation can just reproduce everything?
So it's a little bit hard to reproduce using a single GPU. So I'm been pushing the group to work on large scale setting, and we always trying to see what we can do when we have more GPUs. So kind of the basic units for training a model is like 8 GPUs. So it's yeah. So it's yeah. It's a little bit unfortunate. So yeah. So. But that's our goal, because we believe that computations is key to kind of move the field forward. So that's why we focus on that. I think that's a recent from Paris.
Hello. Yes. I have a question about face frontalization and video compression work of yours. I'm wondering about the key points. If I understand correctly, you are extracting them. They are not basically like a predefined key points, like 68 landmark point, etc. Right? They are like they are learned unsupervisedly. Am I correct? Like, and how do you learn this? How do you learn these key points?
Yes,
especially for the expression.
the expression. Yes. This is a great question. We are using unsupervised learned key points, and I have to say that we are not the first one to use that. I think the first paper can be dated to 2017. The way they do it is that first of all, this key point is learned for the target task. The 68 landmarks, people label the location, and then you train the regressor to regress those landmarks, right? That was how it's trained. For these unsupervised key points, what you do is you want to use this key point to build up correspondence from the reference frame to reconstruct the face. So this key point is optimized for this reconstruction task. Right, so that's you're gonna learn different key points. The second thing, how these key points are learned, right? So that's a trick people has been using is it's more like an equivariant loss. So what you can imagine that if I have my face this, and if I rotate my face by 30 degrees, the key point for reliable method, the key point should be rotated 30 degrees accordingly. Right, so this is a regularization people can use to train those key points, and we do use those regularization. So I hope this answer your question. And actually, the details is in the paper, and I think there are reference implementation from previous method. Yeah.
Thank you very much. That was very clear. Thank you.
Okay.
Okay, any more questions? I think this is a very exciting talk. So if you want to know more technical details, this is a good time and chance. So anyone? Anyone? No?
Don't worry. Yeah.
All right. Yeah. Sure. Go ahead, Ming-Yu.
Yeah, I don't have yeah, I mean, so if you have questions, you can feel free to drop me an emails. I'll be happy to discuss.
Yeah, thank you, Ming-Yu, for the exciting and attractive talk. It's a very impressive. And all right, thank you.
Thank you for
sure. Yeah, talk to you later. So the last thing about this workshop is about the award. So this year, as usual, we have 2 awards. So one is the best paper, and the second one is runner-up. So I'm happy to share the good news with everyone. So this might be very exciting to each participant and also author. First, let me share the screen. So which one do you want to know first, runner-up or best paper award? Anyone? Yeah, I hope at least one author is here when I announce. Otherwise, I have to send out another email to notify everyone. Okay, which one? So let me just release runner-up first. All right, so okay, I'm gonna share my screen. Okay,